You ever wonder how Netflix just knows what movie you'll want to watch next? Or how your phone can squeeze a huge, beautiful photo into a tiny file you can text? Well, behind a ton of that digital magic is this incredible mathematical tool called Singular Value Decomposition, or SVD for short. So what is this hidden algorithm and how is it quietly shaping our world? Let's pull back the curtain.
Okay, so take a look at this image. To you and me, it's a red Corvette. But to a computer, it's not a car at all. It's a matrix, basically a giant spreadsheet of numbers, where every single number represents the color of one tiny pixel.
So that brings up a really important question. If we want to send this picture or save it on our phone, how can we shrink that massive grid of numbers without losing the Corvette-ness of the image? How do we keep the essence but use way less data?
All right, so what happens if we ask SVD to pull out just the single most important piece of information from that entire image? We get this. Yeah, it's just a bunch of blurry stripes. Doesn't look like much, right? But believe it or not, this hot mess is the key to everything. To understand why, we gotta look at what SVD is actually doing under the hood.
This gets us to the core of it all. At its heart, SVD is a way of taking something that looks really complex, like that huge matrix of pixels, and breaking it down into its simplest, most fundamental parts. It's like finding the basic ingredients in a complicated recipe.
And the best way to wrap your head around this is with a picture. Imagine we've got a perfect circle. When we apply a matrix to it, that matrix can stretch, squash, and rotate the circle, turning it into an ellipse. This whole transformation can look pretty chaotic.
But here's the absolute genius of SVD. It proves that any of these complex transformations, no matter how wild they seem, can be broken down into just three incredibly simple, separate actions.
And what are those three actions? It's always the same simple recipe. A rotation, followed by a scaling. That's just a stretch or a squish, and then one last rotation. That's it. That's the whole playbook.
So how do those three simple moves combine to create something that looks so complex? Let's actually walk through it step by step with our circle and ellipse.
We start with our plain old circle. Step 1 is the first rotation. We're not changing its shape at all. We're just turning it, kind of lining it up perfectly for the next step. Step 2, the scaling. This is the main event. Now that the circle is lined up just right, we stretch it along one axis and squish it along the other, and boom, it's not a circle anymore. This is the moment it becomes an ellipse.
And for the grand finale, step 3, a second rotation. We just take our brand new ellipse and spin it into its final position. And just like that, the complex transformation is done. But it wasn't one move. It was just those three simple steps in a row.
Okay, so now that we get the visual intuition, let's connect it to the actual math. Each of those three steps we just saw, the rotation, the scaling, and the final rotation, is represented by its own special matrix.
And this right here is the formal definition. It just says that any matrix, which we'll call M, can be broken down or factorized into these three other matrices multiplied together, U, sigma, and V star. So let's see what each one of them actually does. This table maps perfectly to what we just saw. That V star matrix, that handles the first rotation. The sigma matrix, that's the one doing all the scaling and stretching. And the U matrix, it performs that final rotation. Simple as that. But the real star of the show here, the most valuable player, is that middle matrix, sigma. The numbers inside it are called singular values, and you could think of them as telling you how much to stretch in each direction. The biggest singular values represent the most important information. This is so critical that the number of these non-zero values actually tells you the rank of the matrix, which is just a fancy way of saying how much unique, useful information it really contains.
Okay, enough with the theory. How does all this rotating and stretching circle stuff help us with our blurry Corvette? Let's go back to our picture and see this thing in action.
Remember that awful rank 1 image? Well, SVD ranks those singular values, those stretch amounts, from most important to least. So what if instead of 1, we take the top 10 most important components and add them back together? All of a sudden, hey, a car is starting to appear. We're rebuilding the image using only the 10 most significant pieces of data. Now let's really crank it up. What happens if we use the top 100 components? Look at that. It's almost impossible to tell it apart from the original. But here's the amazing part. We've recreated a high-quality photo using just a fraction of the original data.
That, my friends, is efficient compression in a nutshell.
This technique actually has a name. It's called low-rank matrix approximation. It's this core idea of capturing the soul of something complex by only using its most significant parts, those biggest stretches and their rotations. It's about getting almost the entire picture without having to store all the data.
And this trick of finding the most important components goes so far beyond just images. It is the engine behind those recommender systems on Netflix and Amazon. It's a cornerstone of data science in a tool called PCA. It helps computers understand human language, and it even pops up in mind-bendingly complex fields like quantum computing and weather forecasting. In every single case, it's all about finding the essential signal buried in all the noise.
So, as we wrap this up, what's the big takeaway? Why does this one mathematical idea matter so much in so many different places?
The true power of SVD is its incredible ability to look at any giant collection of data and tell you exactly what its most fundamental building blocks are. And, this is the critical part, it then ranks them for you, from most to least important.
Think of it like this. In pretty much any data set, you've got the main signal, the stuff that really matters, then you have some less important details, and finally, you have a bunch of background noise. SVD is the ultimate tool for cleanly separating that crucial signal from all the noise.
Ultimately, SVD gives us a kind of mathematical X-ray vision, letting us see the hidden structure and the most important patterns in a vast sea of data. And the question that leaves us with is, as our world generates more and more data, what other incredible, important patterns are just waiting out there for us to uncover?